In this ICFD++ example, we are going to demonstrate a 2D store separation example using the new Integral Computational Multiphysics Advanced User Interface, or ICMP AUI. Before diving into this example, I will briefly cover the new features and components of the ICFD++ AUI for first-time users. For more in-depth understanding of the ICMP AUI features common across all Metacom software, please click on the ICMP AUI demo link that pops up on the left side of the video, or refer to the ICMP AUI section of your ICFD++ documentation. The ICFD++ interface is composed of the menu bar, where the mouse is currently moving, the toolbar, which has shortcuts to the commonly used functions and visualization controls, the canvas, in which a geometry or solution is displayed, and the notebook, currently showing that you are in the ICFD++ simulation setup tree. Within the notebook, ICFD++ has its action tree or setup wizard on the left here, which will guide you logically through the various steps of the problem setup, and one or more information trees, in this case, the groups and boundary families tree right here, and the boundary conditions tree over here. Corresponding to each item or step in an action tree or information tree is its action panel, where the user is given the relevant choices based upon choices made in previous and current panels. All panels are dockable and resizable. In the canvas section of the AUI, we can control the display of the grid and grid boundaries. In order to move the geometry around, we can use the cursor and various mouse buttons. So if we left click, that produces a 3D rotation. If we middle click, that is a pan or translate function. And if we right click and move upward, we zoom in, or we can move downward to zoom out. And also holding down the right mouse button, if we move left to right, we can do an in-plane rotation rather than a 3D rotation. Before I proceed to describe the problem setup from scratch, I want to explain a little bit about what we're trying to simulate here. So we have a 2D geometry, and we have two different meshes. So this is an overset mesh topology here. And on the larger mesh, or background mesh, which I'll zoom out here so you can see the entire mesh, we have a simple 2D airfoil type of geometry, which could serve as our, for instance, simplified aircraft geometry in this particular case. And we also have the overset mesh block here, which is the mesh around the store geometry. And in this problem, we're going to work on both setting up the overset mesh connectivity for the case, as well as defining the 6 degree of freedom properties for the body, and simulating the free body motion of the store under the influence of aerodynamic and gravitational forces. And finally, we're also going to utilize the external aerodynamic wizard in order to set up this problem quickly from the start. So now I'm going to close out this AUI window and open up a new window so that we can start the problem setup from scratch. Now, in the first stage of the problem setup, we're just going to be doing a steady state computation so that we can compute the initial condition that we're going to use for the eventual transient simulation. So for the entire first stage of the process, we'll just be setting up the steady state computation. So I've opened the AUI and in the working directory, so we don't have to change the directory that we're using to start with. So I'm just going to go ahead and click OK. And we're at first warned that we don't have any grid files in the current directory. Now, the reason for that is because we have to start by concatenating the grid files together. So I'm going to walk you through that process first. If we go to the Tools menu here, and then we go to Grid Files Manipulation, and you'll see Create New Topology, and we can go down to Concatenate, and select the first option there, which is using subdirectories. So we have two subdirectories in this particular working directory, which we can choose now in the subdirectory tree. So I'm going to highlight subdirectories, and I'm going to click on the plus button twice because we have two subdirectories. And I'm going to also take the checkboxes there in order to utilize both of these subdirectories, and I need to define what subdirectories they are. So I'll highlight the first one, and I can either specify the entire path or just specify the name of the subdirectory. Expanding our menu, we can see that there's a browse button. So we can select the browse button, and you can see there are two main subdirectories here. We can ignore the additional one that says mlog for now. Go ahead and double click on airfoil and click open. Then let's highlight subdirectory 2, click the browse button, go ahead and double click on store and click open. And now we just need to click the run button to run the tool. And once it completes the concatenation process, it will ask us, would we like to run the grid analysis tool? So we can go ahead and click yes. And then it's letting us know that it wants to create an external boundary groups file, which enables us to view the boundaries and the mesh of the particular groups in the AUI. So that can help us with the setup process. So we'll go ahead and click yes there. And we're presented with some statistics about our grid. As you can see here, the total number of groups is 2, and you can see the names of the families and number of faces. We can go ahead and click OK there. And let's click yes to go ahead and display the boundaries. And finally, we can dismiss the concatenation menu. And we now arrive at the cell types and volumes action panel on the left here. So this is just presenting us with some information that's already been read about our particular grid. So we can click OK. And it takes us back now to the basic grid settings. We can click OK once again. And OK once again. Okay, so now we're finished with loading in the grid files. We can take a look once again at our grid to see what it looks like. By default, we only see the grid boundaries, but if you'd like to toggle on the display of the grid itself, you can click on the toggle 2D button up here in the toolbar. And additionally, if you'd like to look at the groups information, we can expand the groups tree and click on the individual group numbers in order to highlight the particular groups. So group 1, as you can see, is the background group or far field group, and group 2 is the store group. Now, in order to proceed with the problem setup here, we are going to start off by using one of the wizards in order to quickly set up the free stream conditions and a lot of aspects of the problem setup. So I'm going to go ahead and click yes for this option. For the wizard type, I'm going to use the default external arrow wizard and click OK. And now we come to the external arrow wizard setup panel here. For this problem, we're going to use SI units, so I won't change that option there. And I will input parameters based on Mach number and altitude. For the Mach number, I'm going to change it to 0.5. And I'm not going to change the altitude. I'm going to leave it as the default value of 10 kilometers. Then if we skip down to the option here where it says the angle alpha is in, that's referring to the angle of attack. And in which plane is it defined? Well, this is a simple 2D problem, and we only have our grid in the XY plane, as you can see here if you look at the axes. So I'm going to change this option to XY plane so that if we were to define an angle of attack, we would have X and Y components only. But then for the pitch angle, the angle of attack here, I'm just going to leave it at 0 actually. So we won't be specifying an angle of attack in this problem. We'll only have flow in the positive X direction. I have the option of selecting a turbulence model, but I'm going to leave it as the default realizable K epsilon. Then we also want to input some parameters for the turbulence initialization. For the turbulence intensity type, I'm going to use the free flight option, which automatically invokes an appropriate turbulence intensity associated with ambient atmosphere, free flight type of problem. And I'll leave the turbulent to laminar viscosity ratio at its default value of 50. And we can go ahead and let's expand the option here where it says show steps. If we expand this little panel here, it explains to us what the AUI is going to do to set up the problem based upon these parameters that we have input here. So you can see that type of equation set that's going to be selected, that it's going to set up our initial conditions for us, initialize the turbulence, select air as the working gas, and set up some basic numerical settings, time integrations, and so on. So we can now click OK in order to proceed. And you can say it quickly jumps to the end of the tree, but then once we click OK, it will go back and ask us some additional questions about the problem here. So that was a quick and automated way to fill out most of the action tree that's required to set up a problem. But there are a few additional steps we should take in order to customize and complete the problem setup. So the first one is additional specifications here. And there are two options here that are relevant to this problem. One is setting up grid motion and Six-DOF controls. The other is setting up the cell cutting and blanking for the overset grid methodology. Now, since this initial stage is only a steady state problem, we're not going to turn on the grid motion or the Six-DOF controls just yet. So for the steady state problem, I'm only going to click yes for the perform cell cutting and blanking. And after I do that, I'll click OK. And we come immediately to the cutting and blanking controls. Now, I encourage you to go to the user manual and read some more background about the overset grid methodology, since I don't have time to go over all of it during this tutorial, where I'm more focused on the setup process. But the basic idea here is we want to use one of the store boundaries in order to cut a hole in the background mesh, and most importantly, blank out the cells of the background mesh that fall inside the store body. But we can also blank out additional cells in order to minimize the amount of overlap between the two grids. In order to do that, we're actually going to use the zonal boundary, which is the blue boundary here on the store grid. We're going to use the zonal boundary in order to cut a hole in the background mesh. So the zonal boundary is going to act like a cookie cutter for us and cut a hole in that background mesh. You'll see in the cutting controls here that the heading here says ranks. In CFD++, we have a sequential cutting process, so you can actually set up multiple cutting ranks and do a step-by-step type of approach, which is very helpful for complex cutting problems. But for a simple case such as this, where the bodies aren't close together, they're not intersecting, and we only have the background mesh inside one of the bodies, it's not necessary to set up multiple ranks, so we'll be able to do everything just with one single rank of cuts. So I'm going to click on the plus button there to add a new rank, and this will produce cell cutting rank 1. I'm going to highlight cell cutting rank 1. And the first question here is, do we want to retain the cut cells? Well, since we're cutting with a zonal boundary, we do need to retain the cut cells. The cut cells are the cells of the background mesh that intersect the cutter boundary. And we want to retain those cells so that we can have a small overlap between the overset and background meshes. On the other hand, if we happen to be cutting with non-zonal boundaries, such as wall boundaries, in that case, we would not want to retain cut cells because we wouldn't want those cells to protrude inside the body and look for zonal connections inside the body. So in this particular case, though, we will retain the cut cells because we're cutting with the zonal boundary. Then we can skip down here to where we specify the boundaries to be used as cutters. And I'm just going to select the zonal boundary. You can see when I select the zonal boundary that it highlights that boundary in yellow, so you know exactly which boundary is being selected to act as the cutter boundary. Then we have to specify the group that's going to be cut. Now, of course, we want to cut the background group here. So which group is the background group? Well, we can simply check in our group tree. If we click on group 1, you can see it highlights the background group. So that's the group we want to cut. So we'll check the group 1 box. And then finally, we're going to need to define some live boundaries. So what does that mean? Well, that means the portion of the cell group that's being cut that we want to remain live at all times. Now, in this particular case, our zonal boundary does not intersect with the airfoil boundary, nor does it intersect with the other far field boundary either, which is outside of the canvas right now. And then the motion of the store should carry it downward, so we most likely don't have to worry too much about this zonal boundary intersecting with the airfoil boundary and cutting across that airfoil boundary. So we can go ahead and just select the airfoil boundary and the outer boundary as well as our live boundaries. It's only necessary to select live boundaries on the group that is being cut, which is group 1. So both of those we can say are going to remain live. And then when the cutting process begins, it's going to determine what are the cut cells that intersect with the cutter boundary. It's going to mark those as cut cells, and we specified at the top that we want to retain the cut cells. Then it's going to mark all of the cells adjacent to the live boundaries as live cells, and it will recursively march through all of the neighboring cells in the domain. And if those neighboring cells are untagged, they will be tagged as live, but anything that's already tagged as a cut cell cannot be changed. So therefore, we have cordoned off a set of cells belonging to the background mesh that will remain untagged. And once we proceed, those cells will be blanked out or orphanized, so they will not be included in the flow calculation. So now we've completed the grid cutting setup process. We can click OK. And then we're brought to the physics source terms menu. We're not going to define any special source terms for this problem, so I'll click OK once again. And we come to the boundary conditions menu. Now you'll see some red X's of boundary conditions that have not yet been defined, and you'll also see a couple of green check marks. Now I'll explain what those green check marks are in a moment, but let's first work on these first four boundaries, which are the original boundaries in our mesh. So you can't see the outer boundary right now, but when we click on these boundaries in the boundary family tree, they're highlighted in white in the canvas. So for the airfoil, that's just going to be a wall type of boundary. So in order to define that boundary condition, I'm going to highlight the airfoil boundary family in the action panel, and I'm going to drag it to the wall category of boundary condition. So this is just a category that I'm placing it in. And after I release, then I have to complete the description of this particular boundary condition. So the default here says a viscous solve-to-wall adiabatic boundary condition. But for this particular case, I'm not going to do a direct solve-to-wall integration. I'm going to use a turbulent wall function instead. So I'll select the wall function and click OK. And you'll see that under the wall category, it creates a particular boundary condition definition, which is called wall BC1. And the airfoil boundary family has been associated with that boundary condition definition. Now the store boundary is also a wall boundary, and I can use the same boundary condition definition for the store as well. So I'm just going to drag the store family over to that particular boundary condition definition. So I'm just going to drag it here and release. Again, I'm left clicking when I drag and drop, same as you would on most types of interfaces. So once I release, it includes the store family with that boundary condition definition. So both of those boundaries will have an adiabatic wall function. Boundary condition number 2, boundary family number 2, is the outer boundary. That's our far field boundary. And this is an open type of boundary. So I'm going to drag that to the open category and release. Since this is a far field boundary with a free stream velocity, it will be an inflow and outflow type. It completely encircles the domain, so it's both inflow and outflow. And I am going to use a primitive variables type of definition, specifying pressure, temperature, and velocities, as well as turbulence variables. For the applied condition type, the most common choice for a far field boundary condition is the characteristics-based boundary condition. So I'm going to select the characteristics-based treatment. And then finally, I need to select an information set with the particular quantities that correspond with the far field or free stream conditions. Now you'll see, because we used the external arrow wizard, we already have a couple of information sets defined here. Now the reason there are two is because optionally we can use just one for the initial conditions and another one for the far field boundary conditions. But the truth is it's assigned the same conditions to both of these information sets. So it doesn't really matter which one we choose. I'm going to go ahead and toggle the first one here. So we want to fill the circle there to select the first information set. The only thing to consider is that you're aware that if this information set is also being used by the initial conditions, then you're essentially coupling this boundary condition with the same conditions that are used in the initial condition. So if at some point you decide to change some values in this information set, it would also change the values in the initial conditions. If you use a completely different information set, then you're deep coupling those two features, and you can change the conditions of one without changing the conditions of the other. So once I've selected that information set, I'll click OK. And that completes the definition for the outer boundary. And you can see that if I hover the cursor over the boundary family, it gives us a synopsis of the conditions that will be used. These free stream conditions came from our inputs to the external arrow wizard. So based upon the altitude and Mach number and angle of attack that we chose, it set up a particular atmospheric pressure and atmospheric temperature. as well as the x and y velocities with a y velocity of 0 here. And it also utilized the input turbulence parameters that we specified to initialize k and epsilon. Finally, we have our zonal boundary condition. Now this is an important boundary condition. It will be communicating flow information between the two groups. So for the zonal boundary condition, we'll drag it to the zonal category. And I have to specify here the zonal connection type. Now this is an overset boundary, so I'll want to choose one of the overset options. It would be perfectly fine to select either of the second two. I could specify it as overset only, but the patched and overset option is a little bit more robust because it will first check for overset connections, and if it can't find any, it would apply a patched type of connection. Now, I'm not going to describe exactly what those mean in detail, but I do recommend that if you're not certain about these terms, that you read through the user manual to understand what they mean. So I'll select the patched and overset option there, and the rest of the options I'll leave in their default state. You can see that most importantly, the condition that's being applied is a simple flow-through condition. So the flow will be able to pass through this boundary without being perturbed in any way. So we can then just click OK, and that completes the boundary condition setup. Now, as I mentioned before, we have two additional boundary families at the bottom that have been created. These are automatically created by the grid cutting and blanking setup process. For each rank that we create, it creates one new boundary condition, boundary family, and that boundary family corresponds to the new family that will be created once we cut out a hole in this background mesh. Because when we cut a hole in the background mesh, there will be a voided region in here of the background mesh, and it will have a boundary associated with it as well. And so, of course, we have to apply a boundary condition to that boundary. The default, which has already been selected, is to assign, as you can see here, this first boundary BC cut rank 1, assign it as a zonal BC. And if we open that BC definition, you can see what was assigned. So again, it was assigned patched and overset. I'll skip to the bottom here quickly to show you it's, again, simple flow through. But you can also see that it selected the option here, allow for an alternate BC when zonal BC fails to connect. So that means if there's any problem with finding connections between the two mesh blocks, then it will resort to an alternate boundary condition, which can be applied to the particular boundary faces that fail to find a connection with the other cell group. So here you can see that an alternate boundary was defined, and that alternate boundary family is in number 6. Number 6 was also automatically created by the cutting process. So it creates these pairs of a zonal boundary and an alternate to the zonal boundary. If we click OK or cancel, it doesn't matter, we haven't changed anything there, then we can then look at what type of boundary condition has been assigned for the final boundary, which is the alternate boundary family. So if I open this panel, you can see that the boundary condition is simply a zonal patch and overset flow through boundary, just like we assigned for boundary family number 3. So what that means is if BC5, the original BC created by cutting, cannot find a connection with the other cell group, then it will move just the faces that fail to connect to boundary family number 6 and apply this boundary condition. Now, since this is also just the same type of zonal boundary condition, that implies that it will fail. If there were any initial failures, they will fail once again in boundary condition number 6. But this is helpful for two reasons to have this alternate boundary family. One is it helps with debugging. It makes it easier to visualize those failed faces if we have the alternate boundary family there, even if it's the same basic boundary condition that's applied, minus the alternate BC. But optionally, if we continue to have problems and decide it's appropriate, we could change this boundary condition to, for instance, a wall boundary. Now that could be because we just have a few faces here and there that over the course of a long transient run fail from time to time, and we just want to make those a wall or maybe a centroidal extrapolation, something like that, just so we can continue with the calculation without a total failure. That would be an option. And other times you might have wall boundaries that intersect each other, and anytime you have wall boundaries intersecting each other, it's absolutely essential that you utilize an alternate wall boundary condition. But that's getting a little too advanced, so let's just accept the boundary conditions that have already been applied and proceed here. So I'll click OK. And after the boundary conditions, we come to the zonal connectivity options. These options control some very specific and advanced behavior about how the zonal connections are achieved between the two grids and how we compute the fluxes at the zonal boundaries. I'm not going to go into detail about these options. Again, I just recommend that you read the user manual if you have any questions about these. But in general, the default options are adequate for many overset cases. So we can click OK again. And we come to the turbulence control panel. Since we did specify that this is a turbulent flow problem and selected a RANS model, and we also selected wall function boundary conditions, you'll see controls related to both the turbulence model and the wall function here. We're going to accept all the default settings and proceed. And now we come to the simulation strategy that's related to the time integration. And so here we just have some basic options. Is this a restart? Well, no, we're starting this case from scratch. How many steps are we going to run here? We'll use the default 500 steps for this initial steady state computation. And we'll also leave the default value of 5 orders of magnitude convergence for run termination. So then we can click OK. And we come to some more time integration settings. Now, again, most of these numerical settings were defined for us by the external arrow wizard. So we actually don't need to change any of these options. It's already selected an appropriate Courant number ramping schedule based upon the Mach number and altitude that we selected. So we can click OK to proceed again. And now we come to the spatial discretization panel. Again, we won't make any changes here. We will maintain the second order accurate and viscid discretization and leave the dimensionality as just simple 2D. So I'll click OK. So now we've finished with the basic physics setup of the problem. We've initialized the flow field, set up our boundary conditions, and finished with the numerical settings. So now we just have the output options to specify. In this panel, the neutral plot file options, we can specify which variables are going to be output to the default plotting file that CFD++ outputs. And we have several different categories of variables that we can specify here. So there are some that will be output by default anyway, unless otherwise specified. But we can add in some variables here. For instance, if we want to output the pressure coefficient, we can check the box next to pressure coefficient. And of course, you would need reference quantities if you're outputting a pressure coefficient. So we can click on the reference quantities button, and we could input them manually, the reference pressure, density, and velocity, or we could simply check the compute references option and select one of the information sets that is associated with the free stream conditions. In this case, both information sets are associated with the free stream, so either one of them would be appropriate, and we can click OK. Another variable that we might want to output is if we select the turbulence menu there. K and epsilon will already be output by default, but it can be helpful, for instance, to output the ratio of turbulent to laminar viscosity. So I'll select that there. That can be helpful to see, for instance, how much your eddy viscosity is decaying in the free stream in order to make sure that your flow is not laminarizing upstream of the airfoil and store bodies. So once we're finished with that, we can go ahead and click OK. And then we're prompted to copy the neutral plot file options to the basic plot output options, which are used for output of third-party solution files. So we can just click OK there. And finally, we have some options related to the probe and output files. So by default, we're going to be outputting the neutral plot file every 200 steps and just overwriting the same default neutral plot file every 200 steps. As for the solution restart file, the default is that it's written out every 100 steps. We won't be changing these options here. There are many other probing options, but what we're really interested in this problem is getting the transient run going, which will happen after the steady state run, and getting a lot of the Six-DOF output data. So that's what the focus will be in this particular example. So let's go ahead and click OK. And finally, the last step to complete here is to save the input file. So I'll just click OK. And that will save the input file that will be used by the solver to control the run. Now, before we go ahead and run this case, there's one thing that I want to show you, which is, we set up the grid cutting and blanking, but sometimes you want to be able to test the grid cutting and blanking before you run the simulation to make sure that everything is working properly. So in order to do that, we can go to the Tools menu, and then we can go down to the Grid Files Manipulation menu, go to Create New Topology, and go down to where it says cut over set grid. So we can select cut over set grid, and we have some options to choose here. First of all, I'd like to select double precision. I usually recommend running most of your cases in double precision. And once we've done that, we can leave the rest of the default options and click run to run this tool. The default mode is to run it on a single CPU. If you have a larger case, it might be necessary to use the multi-CPU tool. So you can see that an information panel pops up, which tells us that folders and files have been created under the OSViz subfolder. So we can go into that subfolder and inspect the results of our grid cutting process. So I'll click OK here and dismiss. Okay, and so after you inspect the cut grid, which you can do on your own in the OSViz subdirectory, if everything looks okay, then we can go ahead and run the computation. So once again, I'll go to the Tools menu, select Run CFD++ in order to run the flow solver, and I'll accept the default options here for double precision on a single CPU and click the Run button. And if we set everything up properly, it should start to run. And once it has run a few steps, we can also monitor the convergence by going to the Results, Solution, Probing, Plotting menu here, then going to Residual Plotting and Steady State Runs. And as the case runs, you can periodically refresh the residuals in order to update them. So that concludes the setup of the steady state portion of the simulation. We'll now focus on setting up the Six-DOF transient simulation. So I have now opened the AUI in the Six-DOF subdirectory. And in the Six-DOF subdirectory, I have copied the grid files from the original steady state run, as well as the solution restart file, which is called cdepsout.bin, and all of the input files, most importantly, mcfd.inp, as well as all of the other files that have a .inp extension. So if you copy those files to the Six-DOF subdirectory, then we can load those files in the AUI and start modifying the setup so that we can run a transient computation restarting from the steady state solution. So since I've opened the AUI in this subdirectory, I don't need to change the working directory. So I'll go ahead and click OK. And once again, we're prompted to create the external boundary groups file so that we can display groups. I've already copied this into the subdirectory, but if you haven't, it doesn't hurt to go ahead and click yes to create it again. If you have a very large mesh, that can take a little bit of time, but for smaller meshes, it's pretty trivial to create it again. So now we're prompted to load in the existing input file. So I'll click OK to do that and load in the steady state setup. And of course, the steady state setup is a complete setup. So you see all of the action items are already checked in the action tree. But we're going to go back to some particular panels and make some changes. So the first panel I'm going to go to is the basic CFD problem definition panel. And I'm going to change the nature of the simulation from steady state to transient. And then once I've done that, I'm just going to click OK. And it advances me to the equation properties panel. But really, before I go that far, there's some other changes that I want to make. So after the CFD problem definition panel, there is the additional specifications panel. I'm going to go back to that panel. This is where we specified that we want to do cell cutting and blanking. And this time, I'm also going to turn on the grid motion, including Six-DOF. So I'll select yes to turn on the grid motion. And then below that, I can specify either Six-DOF or other types of motion. This would usually be prescribed time-dependent motion. In this case, I'll select yes to activate Six-DOF based motion, and then click OK to proceed once again. And now I arrive once again in the equation properties panel. It prompts us again to confirm this panel because now that we've changed to a transient type of simulation, it would be possible if we wanted to invoke a large eddy simulation type of approach, but we'll continue with an unsteady RANS approach here. So I'll just click OK. Then we're prompted to confirm the fluid properties. I'm not going to change anything here. If we open up the panel, you can see that air is still selected by default. So we can just click OK in order to confirm air as our working fluid. And now finally we come to the Six-DOF body specification action panel. Okay, so I'm going to walk you through the process of setting up the Six-DOF portion of this simulation. So the first question is this a restart for Six-DOF? So even though we are restarting this run from the steady state solution, we're restarting the flow solution, this is not a restart for the Six-DOF. We are defining the initial conditions here in this panel for the Six-DOF body. It's only a restart for the flow solution. So I'll leave that set as no because we haven't run any Six-DOF steps yet. There is a new restart mode. I'm not going to discuss that here, but you can read about it more in the user manual. Next, we come to the option turn on Six-DOF probes. This option provides us with a lot of output related to the Six-DOF motion. So that includes the position and orientation of the body, time-dependent, as well as time-dependent forces and moments, time-dependent velocities, and so on and so forth. So you get a lot of information about the trajectory and motion of the body throughout the computation. So we'll select yes here because that's the main output that we're really interested in getting from this computation. And then you can specify an interval of output for this Six-DOF probe. And we want output at every step. So I'm going to go ahead and leave that as 1 for the interval of output. Then we can specify a gravitational acceleration and a particular magnitude and direction for that. In this case, we simply have a 2D case, and gravity, as you can see here, positive y is in the upward direction. So gravity will be working in the negative y direction. So I'm going to change the default here, which has the x, y, and z components of the gravitational acceleration vector. And I'm going to specify negative 9.81 for the y component and 0 for the z component. So these are some general Six-DOF settings. And now we want to define settings that are specific to our Six-DOF body. You'll see the Six-DOF body specification tree down here. It's possible to define multiple Six-DOF bodies that can all be moving separately from one another, that have their own body properties and so on. Or it's also possible to define, for instance, an assembly of cell groups that move together as one Six-DOF body. Both of those types of things are possible. This case is much simpler. We have one cell group that pertains to our store, and we have only one Six-DOF body. The airfoil will remain stationary in the global coordinate system, so it's not going to be moving relative to the global coordinate system, only the store will. So I'm going to go ahead and first check the checkbox there next to Six-DOF body specification 1, and then I'm going to highlight the first entry in the tree there and click on the edit button. And when I do that, the Six-DOF body specification panel appears. So I'm just going to expand this panel a little bit so we can see all of the controls. So the first option there is to turn on internal CFD++ RBD for rigid body dynamics coupling mode. By default, this is set to yes. So this is the standard CFD++ coupled Six-DOF approach. There are some other special options associated with these first two choices here. I'm not going to get into the details of those, but you can read about them in the user manual. Then we have the choice of specifying a body name. This is for cosmetic purposes only. It's not a required step. Then we must specify how many cell groups are included in this particular Six-DOF body. Is it just a single group, or is it multiple groups, in which case we need to specify all of the individual cell groups that are included in the Six-DOF body that would be moving together. In this case, our Six-DOF body only has one single cell group, so we'll leave that as single group. And then we need to specify which group is it that will be moved based upon the Six-DOF forces and Six-DOF properties. So that's easy enough to check. We can come over once again to the groups tree, and let's highlight first of all group 1, and maybe it's easier if we also toggle on the 2D grid display. And you can see that group 1 is the background mesh, so we don't want to move the background mesh. It's group 2 that is the store mesh, and that's the group that we want to move under the Six-DOF controls. I will specify group 2 here. The next choice is to define the Six-DOF body. What are the boundaries that constitute the Six-DOF body? So if we look over here at our boundary family tree, and let me unhighlight the groups. So if we look over here at our boundary family tree, we can click on the store boundary, and you can see that one single boundary completely defines the body. the store body. Now it's not completely defining the group, we've already specified the group, but that completely defines the store body. And this is the boundary on which the forces and moments will be computed that will then be used in order to compute the acceleration of the body. So we only need to specify the store boundary family here, which is boundary family number 4, and then we can proceed to setting up the body properties. Now you can see for the body properties there are 2 columns with a beginning time and an end time. So you can specify properties at the beginning of the simulation as well as the end of the simulation. Now really, this just applies a ramp function. So the beginning time doesn't have to be 0. It could be a later time. And at all times prior to the beginning time, it will use whatever properties are specified in the left column. And at all times after the end time, it will use whatever properties are specified in the right column. And in between, it will perform a linear interpolation. For this particular problem, what are the properties that we're going to specify for this store? So first of all, I'm going to use a mass of 2,000 kilograms. And right now I'm only working on the left-hand side column here. So I input 2,000 kilograms for the mass. I need to specify the center of mass also. So we can look at the coordinates to get a rough idea of where the center of mass is. So once I toggle on the grid display, I can hover the cursor around and you can see in the left-hand corner of the AUI, you can see the output of the coordinates where the cursor is located. So I can hover the cursor around and we can see roughly the position where you might define a center of mass. What I'm going to do is specify the center of mass as x equals 4.8 and y equals -2. And then we have to specify our moments of inertia. The truth of the matter is that in this case, because it's a 2D case, the only moment of inertia input that matters is the z moment of inertia, which I'll explain a bit more later. And for this particular case, we're actually going to leave the default value of 1 for the moment of inertia. Now, it's rare we'd do that, but it just so happens that in this particular case, it provides a reasonable value and a reasonable motion for this store. Now, of course, we must specify the conditions at the end time, but if you want constant conditions throughout the entire simulation, there's a copy button here that says copy beginning to end when you hover the cursor. You can just click on that button and it will copy the beginning conditions to the end conditions as well. So in what type of case would you want to change the conditions? Well, you might have cases where you're doing a fuel burn and the mass, as well as the moments of inertia and possibly the center of mass could change in time as well. In this case, we're not doing anything like that, so we won't be changing those conditions. So if we scroll down a bit, we come to the next option, which is body release time. Here you would have the option of not allowing the body to move until a particular point in time. We're not going to use that option here. There's also a body reference pressure. For a closed body, the reference pressure should be inconsequential. But if you had, for instance, a symmetry plane and the body's moving on the symmetry plane and you wanted more meaningful force output, then you might want to specify the atmospheric pressure in this particular input. But it's not important in this problem because we have a closed body, so the pressure differential will not change whether or not you use a reference pressure. Then we come to the next input, which is called initial origin of body coordinate system in the inertial coordinates. This is basically just an initial offset from the currently displayed grid position. So if you want your initial position at time 0 to be something other than what is displayed here, you can specify that translational offset in this input box here. However, we've already run a steady state solution here that we're restarting from, so you definitely would not want to do this after you've already run a steady state simulation. You'd want to do this and then rerun a steady state simulation. You have the options to input initial translational and rotational velocities if you don't want to start with a velocity of 0. We won't be doing that here. We'll start with a velocity of 0 and let the body accelerate based upon aerodynamic and gravitational forces. And then we also have the option to input the orientation of the body based either on unit vectors or Euler angles here. But the body is already in the position that we want it to be in. So again, we're not making any changes there. We'll use the initial position as displayed in the grid. And then finally, we come to constraints on forces, moments, and the motion of the body. Since this is a 2D example, this is actually a 3 degree of freedom case rather than 6 degrees of freedom. Because in 2D cases, you can only have X and Y translation as well as Z rotation. So we're going to go ahead and turn off 3 of the degrees of freedom, which is we're going to turn off translational motion in the z direction or any rotations about x or y parallel axes. In order to do that, then in this first box here where it says inertial frame controls for the constraints, let's go ahead and check the box next to modify aero force in z, modify aero moment in x, and modify aero moment in y. Now the reason it's saying force and moment here is because what we really do in the solver is we compute all of the forces and moments, and then we scale the forces and moments in order to, for example, turn off a particular degree of freedom. So in this case, for the z force, there probably wouldn't be any z force anyway, but just in case, in order to be thorough, we're going to specify 0 as the scale factor. So if there happened to be any non-zero z force for some reason, we'll scale it by a factor of 0, and the z force will disappear. There will be no translational acceleration in the z direction. And we will do the same for the x and y rotations. We will leave untouched the aero forces in the x and y directions and the aero moment in the z direction. So that allows us full 3 degree of freedom motion, which is planar motion for this 2D case. We've defined these constraints in the inertial frame, which is sufficient in this particular type of case. There are also body frame constraints that you could use instead. Those are typically for slightly more advanced computations, but they can come in handy for other cases. And then we also have the option here to say whether or not rotation should be about the center of gravity. If you had, for instance, a hinge rather than a simple free body motion, you could select no here and specify the hinge location and moments of inertia about the hinge. But in this case, we're just doing a simple free body motion, so we'll leave the default of yes for rotation about center of gravity. There is also the option to input external body forces, which could be, for instance, a spring force, or something more general, like you could have an ejector force. If you're doing a store separation case with an ejector on a pylon, you could define that here. And you could also define, for instance, for a projectile, an external force in the body frame that defines a thrust direction vector. Those are all things that are possible, but we're not going to be using those features today. So then, at this point, we've completed the setup for our Six-DOF body. So we can, at the bottom of the panel here, go ahead and click OK. And no need to make any more changes in the main Six-DOF panel, so we'll click OK once again. So when we click OK to proceed, we are prompted by this panel here to copy the Six-DOF input file, which is called mcfd sixdof.inp, to the Six-DOF solution restart file, which is called mcfd sixdof.out. Now in this particular case where we're starting from scratch, it's fine to click yes or no here. But the reason it's asking us to do this is because if by chance you've already run some previous Six-DOF case in this particular working directory, there could be a pre-existing Six-DOF restart file. And when we eventually start the computation, it's going to copy that Six-DOF restart file to the Six-DOF input file and read in the conditions from the Six-DOF input file. Now, if you don't want that to happen, if you're not doing a Six-DOF restart, then of course it's a good idea to go ahead and copy the Six-DOF input file to the Six-DOF output file to make sure that when you start the computation, you have the same conditions in both the input and output file, which are the initial conditions only. So we can go ahead and click yes there. And then we come to the main grid motion control panel. You see a few options here. The main ones that pertain to this problem are right here. Move grid with selected velocities. Yes, this is a transient computation. We are going to be moving the grid in time, so we'll leave that selected. And then recalculate zonal connection at each time step. We are also going to leave that selected as yes. That's because every time step when we move the grid, the solver is going to have to redo the cutting and recompute the zonal connections between the different cell groups. So we can leave the default settings and click OK. We come again to the turbulence control panel. We won't be making any changes, so let's click OK. Then we come to the help set numerics panel. Now, we didn't utilize this panel in the steady state setup because we had already used the external arrow wizard. In any case, when you're not using a wizard, it is a good idea to use this help set numerics wizard to help you get some good best practice settings for your numerical settings. In any case in which you're not using one of the wizards, it's never a bad idea to use this help set numerics panel in order to set up the numerics for your problem. But in this particular case, we still have the same settings from the external arrow wizard in this setup. So we're just going to be tweaking those settings a little bit. So in this particular case, I'm not going to make any changes here. So I'll leave these selected as no and click OK. I come to the Riemann solvers panel. I don't need to make any changes here. We're still operating under the same flow regime, so nothing needs to be changed. But now I come to the simulation strategy. And this is where we really have to change things because we're now doing a transient computation. So first of all, is this a restart? Yes, for the flow solution, this is a restart. It's not a Six-DOF restart, but it's a flow solution restart. So we'll select yes here. We'll input 1,000 steps to run. And otherwise, we'll just leave the default settings, which it's going to utilize a dual time stepping implicit approach. So we'll click OK. The AUI will prompt us to load some default transient settings. Now, in a lot of cases, I'd recommend selecting yes here to get some best practice settings, but I just want to, again, tweak the steady state settings that we already have for this transient run. So I'll click no. And we now come to the time integration panel. First of all, for the first option here, global time step based on Courant number, we'll leave that selected as no. We're going to input our global time step directly. The local time step, however, will still be spatially varying. That's for the inner iterations, not for the physical time step. Then I have the option for the Courant number of either reading it from the restart file or reading it from the settings below. Now, in the steady state computation, we used a maximum Courant number of 100 anyway, so that option would be fine. Since this is the start of a new transient computation, I'll use the values below option to make sure that we utilize whatever settings I specify in the Courant number section here rather than what was in the pre-existing solution restart file from the steady state run. So for the Courant number ramping schedule, since we already have a physical flow solution from the steady state solution, we're going to use a constant Courant number here. So we'll use the same Courant number at every single global time step, which will be a Courant number of 100. So we'll ramp from 100 to 100. That just means it's constant. And then I need to input a global time step size. We'll use a time step of 1 millisecond or 0.001 seconds. I also need to input a particular number of internal iterations per global time step. So at each global time step, we're going to be trying to converge some inner iterations or a pseudo-time iteration. And so we need a certain number of steps to do that. For non-moving mesh cases, often 4 or 5 inner iterations is sufficient. For moving mesh cases, sometimes we need a little bit more. So 10 to 20 inner iterations might be required in order to converge the inner iteration residuals by the desired amount at each time step. So I'm just going to input a value of 10 for this problem. And for the global step inner iteration termination criterion, the default here is 0.1, which corresponds to 1 order of magnitude. Sometimes I drop this just a little bit to a value of 0.05, just in case some of the residuals converge faster than others. Now, there are more advanced options in terms of how to monitor convergence of the inner iterations, whether you want it to be based upon the average of all equation residuals or particular user-specified residuals. And also you can do a more advanced approach where you monitor convergence based upon forces or moments. But in this case, we'll just use these simple settings that I've set up here and go ahead and click OK to proceed. And we come to the neutral plot file options. Again, we'll just output the same solution variables that we did for the steady state run. So I'm not going to be making any changes here. So we can click OK to proceed. And again, click OK to copy those options over to the plot output options file. But here for the probe and output files options, these settings become much more critical when we're dealing with a transient computation because we want to make sure that we get all of the types of solution output that we want throughout the duration of the simulation. So first of all, for the neutral plot file, the default neutral plot file, it's important that we output the neutral plot file with a step number appended to the name so it's not getting overwritten every time and we can have that time accurate data. And I'm going to use a frequency of 10 steps here. And just for consistency, I'll specify a frequency of 10 steps for the default neutral plotting file as well, the one that gets overridden at whatever the specified interval is. Also, now I'm going to go to the solution restart file output options, and I'm going to output the solution restart file, not at the same interval, perhaps we don't need that as often, but I'll output the solution restart file every 100 steps. And once I've done that, I'm going to click OK. And then we come to the end of the problem setup. So here, I'll go ahead and click OK to save the changes that we've made to the input file. And it'll again prompt us. It'll save the Six-DOF input file as well. So you see the additional input file save option there. And again, prompt us to save those input settings to the Six-DOF solution restart file, which is fine at this point. That'll just mean that we have the same settings in both of those. Now, before we go ahead and start the transient computation, there's one additional step that you might want to take that can be convenient when you're doing transient runs that are being restarted from a pre-existing steady state solution. And that is, if we go to the Tools menu and Solution Files Manipulation, then Solution Restart File, you see the option here to reset the step number in the solution restart file, as well as the option to reset the time in the solution restart file. Now, resetting the time is not necessary because the time value in a steady state computation is always 0. It never changes in a steady state computation. So the time will certainly start from 0 in this computation as well. But if you'd like to reset the step number so that the step number restarts from 0 in your transient computation, then go ahead and select Reset Step Number in Solution Restart File. So in the Tool panel, we can input the step number that we'd like to set for the solution restart file. And of course, if we want it to start from the beginning, then we'll set the step number in the restart file to 0. So we can just leave that set as 0 and go ahead and click Run. So you can see in the tool output that the original step number was 353, and we've reset it to 0. So now we can dismiss the tool, and we can go ahead and run the computation, and it will restart from the pre-existing flow solution from step 0. So we'll, from the Tools menu, select Run CFD++, and I'll leave the default settings for a double precision run on a single CPU. And you can see that the case starts to run, and the output will come a little more slowly because it's doing all of those up to 10 sub-iterations per time step. And as the case is running, you might want to monitor the convergence of the inner iteration residuals. So I'll show you how to do that. If we go to the Tools menu, then select Results, Solution, Probing, Plotting, go to Residual Plotting once again, you'll see the Transient Runs option. So we can select inner iteration residuals. And you can see the convergence at each time step. So you can see global iterations here. So from time step 15, 16, and so on, you can see how much the inner iteration residuals are converging. And so that concludes this video tutorial about how to set up a store separation problem in ICFD++. Thank you.